Hey, welcome back. Let's talk about section 7.4. Today it's going to be about parallel lines and proportional parts. So the big thing in this section is that we're going to be dealing with some triangles and some images that are not triangles, but the main thing is the parallel lines. And we're going to be using parallel lines to create proportions and ratios similar to what we've talked about in the previous sections. So go ahead and write this first example down. This is the triangle proportionality theorem, and basically what this theorem tells us is that if we're given a triangle, so here we've got triangle ACD, the largest, and we know we have within that a segment, so here BE, that's parallel to one of the sides, so BE here is parallel to CD. So if we're given this situation, what we can know from this is that this segment has now created two ratios that are equal between the sides. So what this does is it allows us to write that the ratio from A to B, so A, B, over its same side portion, so BC, would have to have the same ratio or relationship as the other side of the triangle. So we'd say it's going to have the same ratio as A to E, so AE, over ED. And what this allows us to do is if we're given some missing parts, then we can fill in our proportion and cross multiply and solve. All right, so it's if you have a parallel line to a side in a triangle, it makes the side lengths of that triangle proportionate. Okay, so this is really useful when you're dealing with art, if you're trying to draw objects that are far away. So if you've ever seen anybody trying to draw something in the distance, they're really using this theorem. We just don't call it that, obviously, when we're in an art class or anything like that, but it's using that concept to know that things are proportionately going to be further and further away to make them look realistic and drawn to scale. Okay, so very helpful in art or scale drawings and things like that. So let's go ahead and draw an example of what that might look like in terms of just basic geometry. So here it says in triangle PQR, they tell us that ST is parallel to RQ. So I'm going to go ahead and mark that just so we know. So ST and RQ are parallel, and that has to be true for this to be a triangle proportionality theorem problem. And so if these are parallel and we have a triangle, now we just have to set up our ratio. So what I would say is that this side, so PT over TQ, is going to have to be equal to, and we do the same thing for the other side, PS over SR. And so all I have to do is just fill in my numbers. So PT was 7.5, and then TQ was 3. And then I do the same thing for the red side. So PS was X, and SR was 2.5. And now we have this nice proportion. All we have to do is go ahead and cross multiply. So if I multiply 7.5 times 2.5, we get 18.75, or 18 3/4, equals 3x. And then, of course, all we have to do is divide both sides by 3. And when we do that, we get x is 6.25. Or you can write it as 6.25. And then always just pay attention to rounding. If they do ask you to round to the nearest tenth, obviously you'd want to make that 6.3. So there's our final answer. So quick proportions, hopefully not too bad. You just have to know what matches up. Next is our converse of the triangle proportionality theorem, and this is just backwards. So basically this is just going to be the opposite of what the original theorem says. So here they might tell you that if HG over GF, so if this portion over this portion is equal to the ratio of PT over TF, okay, so over of this section over TF, then what has to be true? Well, that means that segment HP would have to be parallel to segment GT. So it's just the reverse. All right, so there's no difference really in the concept. It's just backwards. It just all depends on what the problem is asking you. So for example, this particular problem would tell you some information about the side lengths, and they want to know, is DE parallel to GH? So in the end, your answer is going to be yes, it's parallel, or no, it's not. So let's look at our picture and what they give us. So they tell us EH is 3, and they tell us HF is 9. And then they tell us this piece of information here. They tell you that DG is a third of GF. Well, the thing is, we don't know anything about GF or DF. We don't know any lengths here, but what we do know is that this DG is a third of this portion. So if we don't know G to F, we can just call it X. There's no other variables in our equation, so we can put that there. So we don't know its length, and we know that DG was a third of it, so 1/3 of X. So now we have something in its place, and now we can go ahead and set up our rule. So knowing about our proportionality theorem, we can say that 3/9, so this EH over HF, is going to have to be proportionate to, and I'm going to start with the same thing, DG, so 1/3 X, over GF, which was just the X. So notice I matched things up. So I started with the little one so on the first equation, so I start with the little one on the second. And then I can just go ahead and cross multiply. And remember, the goal is to see, are these two things parallel? So when I cross multiply, 3 times X is 3X, and then I get equals 9 times 1/3. Please try to do this without your calculator if you can. Well, 9 and 1/3, the 3 cancels, becomes a 1, and that 9 becomes a 3, so we just get 3x. Well, is 3x equal to 3x? Yes, it is. So this does work, which means that DE would have to be, or segment DE would have to be parallel to segment GH. So this is going to be what they look for. And if they ask you to justify, then your work, you could show here, you get the same thing on each side of the equal sign, and you could have put a check mark next to it. That's showing me that you understand these are equal, so these have to be parallel. And obviously, if you got something different, maybe you said this side was 10x, and then you got over here was 7x, those would not be the same, so you would say that they would not be parallel. Okay, so the goal from the converse is to show that the ratios are the same in order to make things parallel to each other. And if they're not, then they can't be parallel. Next, and this is probably the biggest part of our section, this is about the mid-segment of a triangle. So the mid-segment we've talked about before when we talked about mid-segments of trapezoids, and it's a very similar concept, just a slightly different rule. So remember, a mid-segment is a segment that's connected from the midpoints. So in this triangle here, I've got triangle maybe A, B, C. There are actually 3 different mid-segments that we could draw within this triangle, whereas in a trapezoid we only had 1. So if I want to draw the mid-segment in this triangle, I might go ahead and find my midpoints. So I'm just going to estimate for now. So here's midpoints for each side. So maybe we call this J, K, and L. So a mid-segment is connected by 2 midpoints. So I'm just going to go ahead and draw these in different colors. So one mid-segment might be from J to L. So I'm just connecting 2 midpoints. Another mid-segment might be from L to K. So there. Okay, and then maybe the last mid-segment, I'll do it in green, would have to go from J to K. So notice there's 3 different ones here, and I put them in 3 different colors, and they're each related to the different sides. So if you notice here, if I'm talking about the orange one, so segment JL, it's going to be parallel to the side across from it. So it's actually going to be parallel to segment BC. So there's one. Okay, and my mid-segment JK, so that's the one that's in green, is actually going to be parallel to its side across from it in the triangle. So parallel to, oops, not equal to, parallel to AC. And then the last mid-segment, LK, that's in blue, so segment LK, is going to have to be parallel to the side across from it, which is A to B. So mid-segments in triangles are always parallel to one side, okay? And then the main rule that we're going to have here is that the mid-segment is going to be half the length of the side that it's parallel to. So, for example, if I told you that A to C was 20 inches, then its mid-segment J to K would have to be 10 inches because it's going to be half the length of its parallel side. All right, so hopefully those are going to be pretty quick examples to go through because you just have to know to divide by 2 or multiply by 2, but you have to be able to know which side it goes with. So let's look at an example where we might use the mid-segment. So here it tells you XY and XZ are mid-segments. Okay, and it says you want to solve for xz. So let's do that first. So xz is this one I'm coloring in blue right now. And it said it was a mid-segment, so it's going to have to be parallel to the side across from it. So it's going to be parallel to YT. And make sure you're doing the whole side of the triangle. And they want to find the length of XZ. So they want to know what that is. Well, the good thing is we know that this whole length here from R to T is 13. So we'd say XZ is half of 13. So here we'd say the length of XZ is 6.5, and then we'd be done. So that's really quick. Okay. The other part of this problem is asking about an angle measure. So this is where knowing that things are parallel is going to be very important. So they want you to find the measure of angle RYX. Now, if you don't remember back from the very beginning of first semester how to identify angles, remember this is always the vertex, the middle letter. That's what we care about. So when we follow these letters, we're not talking about all three angles. We're specifically talking about this one created by the other two. So R to Y to X, okay, is what this angle right here. Well, what's useful is knowing that a mid-segment is parallel to a side. So here what we have is this mid-segment at the top, XZ, and it's parallel to its opposite side, RT. So we've got some parallel lines here, and if you remember back from first semester, when we have parallel lines cut by a transversal, we have this nice new thing called alternate interior angles. So they look like that. So alternate interior angles. So that allows us to know what the measures are. And here they gave us this nice thing. They gave us it was 124 degrees on the inside. So automatically the measure of angle RYX would also have to be 124 degrees. And if they ask you why, you would say it's because they are alternate interior angles. And the only reason we know they're alternate interior is because mid-segments are parallel to a side. So we've got two parallel lines here. So that concept of alternate interior, alternate exterior, corresponding, and consecutive interior are still going to be helpful this semester, even though it was last semester topic. Okay, so very important to be able to identify those. All right, we've only got two more theorems to go through and then we'll be done with this section. So this next one is about proportional parts if you're dealing with parallel lines. So here we've got this pretty picture, kind of looks like a map. You guys drew something similar to these when we ended the first semester, and it says if you have 3 or more parallel lines, so here I've got 3 parallel lines, I could have 4, 5, 20, doesn't matter, and then they've got 2 transversals, so remember a transversal just cuts parallel lines, okay, so if you have this kind of situation, then all of those lines are cut proportionally. And remember, proportions are ratios that are equal to each other. So what we could say from this image is that AB over BC, so AB over BC would have to be equal to DE over EF. So we'd say it's equal to DE over EF. Very similar to the first examples theorem, just not with triangles anymore. Now we're just dealing with lines and transversals, so a little bit more generic than the first example. So let's use this to try out some realistic problem. So here, this says you've got a map, and these are particularly representing roads. So it says you've got Lark Street, Maple Street, and Nuthatch Street, and then you've got 2 cross streets that are just your transversals here. And on this map, they tell you the distances between the streets depending on which cross street you're on. So from Lark to Maple, it's 26. From Maple to Nuthatch, it's 13 on this particular road, and then from Nuthatch to Maple on this road, it's 16, maybe we call it miles or something, and then from Maple to Lark on this street is X, and they want us to figure out what would this distance be between these 2 streets. So the key here is that they told us every street, Lark, Maple, and Nuthatch, were parallel. So we've got these nice parallel lines cut by 2 transversals. So this is using the example, the ratios that we just talked about. So I'm just going to set up a proportion. So I'm going to say 26 over 13, so 26 over 13, because they're from the same side, are going to be equal to, and then we're going to do the same for the other side, X over 16. And notice I started with the corresponding parts. So I started with 26, so I'm going to start with the x. So x over 16. And now this is a nice proportion that we can go ahead and solve by cross multiplying. So 26 times 16, that's going to get you 416 equals 13x. And then, of course, we divide both sides by 13. And we get that the distance between Maple and Lark on this side street is going to be 32. And of course, if it has units, you want to make sure you include that as well. So this is between the city blocks. All right? Very short, more proportions, hopefully not too bad to set up as long as you're consistent. And then the last one is same situation, but this time we're talking about congruent parts. So here we still have 3 parallel lines cut by transversals. So let me see if I can move this up just a little bit. So we've got the 3 parallel lines that are here, and I'm always drawing these the same way, but the picture might be turned on its side, so don't let that fool you. Okay, and then we've got the 2 transversals, and here it says if we've got 3 parallel lines with 2 transversals, and they tell us that 2 parts are congruent, so maybe from GH is congruent to HP, they've marked that for you, then that would mean that automatically the other 2 sides would have to be congruent. So these 2 would have to be the same. Now notice they are not the same left to right or side to side. Here they go on the same transversal are congruent. So this would be AB would have to be congruent to BC. All right, so be very careful here. They don't go side to side. It's always along the same transversal. And you can only know this if they've given you markings that they're congruent or something in the directions that allow you to show that they're congruent. So make sure you have that picture drawn. And we're going to just set up one example and then we'll be done. So here, like I said, this picture's kind of turned on its side. In the picture, they would tell you that these are parallel. You have to know that the lines are parallel to be able to do this. And it says solve for x and y. So notice we've got 3 parallel lines. We've got 2 different transversals here. And they told us that these 2 segments are congruent. So that should be the easy part to start. We can go ahead and say that 12 minus 3y, which is this part here, has to be equal to 16 minus 5y. And then you guys should be able to go ahead and solve this down for y at the end. Okay, now where the rule comes in, this new theorem, it says if one side has congruent parts, then the other side has to be congruent parts. So these 2 things here, so 1/4 x plus 6, has to be also equal to that one, so 2x minus 29. So all we'd have to do is just set these equal, solve for x, and then we'd be done. Okay, so really helpful rule that you want to make sure you draw the example in, and then I would of course try to solve for x on those, especially the one with the fraction. That way if you have any questions you can ask me in class. Okay, that's it for this section. It's more ratios and proportions, so if you have any trouble, please feel free to ask me for extra help and you should be good to go. Thanks for listening.